This is a review of our last class. This is a vibration analysis of a spring mass system, free vibration analysis. We have a particle suspended by a spring. The particle is in a uniform gravitational field. The spring is initially unstressed, and we have also we've been given the initial conditions. So we have the initial displacement in the axial direction and the initial velocity equal to 0. So those are the initial conditions and the information we need to model this spring mass system vibration. Here we want to find the displacement as a function of time. So we need to derive an equation to calculate the displacement as a function of time. And also we want to calculate the kinetic energy, the maximum kinetic energy, and the maximum potential energy in the ensuing motion. So this is the schematic of the information we know. So again, this is a particle suspended by a spring. Here's the particle, it has a mass. This is the spring, it has a stiffness, of course. And this spring is attached to a rigid surface. We have gravity acting, and this is the global coordinate system. So we assign the frame of reference at the elevation of the particle for a unstressed spring. This is very important in this problem. This is a very important information. And actually I repeat that here in the assumptions. I say again that the spring is initially unstressed, and in that case, since this is a let's say this is a 0, right? Initial, this is the reference for the motion. So this spring, since it's a unstressed and the particle is moving upwards, so I'm from this configuration, I assume or I understand that the mass is going to move up. So in terms of forces in the system, we have gravity and the spring force imposing resistance to the motion in that positive y direction. So this is the assumption, the major assumption for this problem. Okay, moving to the analysis. The first step is to draw the free body diagram. So it has to be consistent with the schematic. So as you can see here, let me change back to the marker. So this, the free body diagram has to be consistent with the schematic. So the mass, the particle is has two forces acting on it. So we have the weight and we have the spring force. And here we have the reference position. So the starting position for the motion of the particle. Okay, next, with that information and the Newton's law of motion, we can move to the step 2 and write our equation of motion. So the total force in the x direction is minus ky, which is the spring force, minus mass times gravity. This is the weight of the particle, and mass times acceleration. So we just rearrange this equation to get the equation of motion, or equation 1. And finally, we need to solve for this equation, because what we want a displacement y as a function of time. So we need to solve the equation of motion and find this displacement. Well, in this case, we split the solution in 2 parts: the transient solution part and the steady state solution part. So those are the 2 components of the total motion of the mass. In other words, we have the transient solution, or the harmonic motion, and the other component is the steady state solution, or the static displacement. So those are the 2 components of the total displacement of the particle. So then, if we substitute the equation number 2 into equation number 1, which is the equation of motion, or in other words, if we substitute the total displacement into the equation of motion, we can write the equation of motion as in a splitted form in terms of transient and steady state displacement. Now, in terms of steady state displacement, the acceleration is 0, because the steady state is supposed to be static, so we don't have, it's an equilibrium, it's a displacement under the equilibrium, so we don't have acceleration. This acceleration there is 0, and then so we just rewrite the equation here, and if you look at the components here, we have transient, and the static components of the whole equation. So this is, let me go back here. So this is the static portion, right? So in order to get this, the transient components, the summation of the transient components must be equal to 0. So, and that makes sense. So we are splitting this equation in a system of 2 equations. So this is the equation of motion for the transient part, or for the harmonic part of the displacement, and this is the equation of the displacement under equilibrium due to the weight of the mass. So as you can see here, this is the solution of that we have half done here. So we have the static displacement or the steady state displacement. So this is the solution for one component of the total displacement. Okay, so we are done with the static or steady state displacement. The next step is, which is we have to elaborate a little more, is the solution of the equation of motion or the harmonic component of the displacement. So then we need to apply some calculus, right? So the equation, this is a ODE with constant coefficients. So the solution for that is the exponential function e to lambda times t, or times time. So this solution satisfies the this homogeneous ODE, or equation 3. So then all we need to do is to take the first and the second time derivative of this function and substitute them back into equation 3. By doing that, we get, and of course we do some rearrangement here because these terms, they are, they are common terms, so they go to the right hand side and becomes 0. But so we get this equation number 6. This is called the characteristic equation. So this is a quadratic equation, and the solution is in order to solve this equation, we need to calculate or determine the roots of the equation. Well, the problem is when we do that, we have a square root of a negative number, and this means we have a imaginary solution for the root, and that becomes, this problem becomes a complex roots problem. But no worries. The workaround is easy, is straightforward. So we keep going with the general solution for that. So this is the general solution for the harmonic equation of motion. So we have, if you look back here, we have the exponential function multiplied by a constant. So actually we have two components because this is a second order equation. So this is equation 7. So then we just plug the roots that we calculated from the characteristic equation into equation 7, which is the general solution, and then we get a new general solution, equation 8, with our complex roots. All right. Now we need to solve this equation, right? Equation 8. And it looks complicated, but then we have, and thanks to Euler, we have there is a correlation between this exponential function with a imaginary component and the trigonometric functions cosine and sine. So with that correlation, and there's a equation, this is the general solution. If we combine the two, or if we substitute the general solution we got into the Euler formula, we get a new general solution, but now as a function of cosine and sine terms. And then we just work on the common terms here and get this arrangement of that equation, and then we can replace the constant terms by two new constants, a and b. So that's the procedure. And then by doing that, we get the equation 9, which I call a sub-partial solution for the transient displacement or the harmonic displacement. Why sub-partial solution? Because we still need to solve for a and b. Okay. Now, but before we solve for those two constants, we can actually put together the transient and the steady state displacements and get total solution, and I'm going to call it subtotal solution again because we still have to solve for a and b, but this is the complete displacement for this mass spring system. Now the procedure to eliminate, or not to eliminate, but to solve for those two constants, we know very well. We apply the initial conditions, right? So again, the initial conditions are the initial displacement at time 0. So if we substitute that into equation 10, we get A equal to the initial displacement plus mass times gravity over stiffness. So this is displacement and this is displacement. This second one here is the mg over k is actually for the spring force over the spring stiffness. So this is the displacement of the spring displacement. So then we have the solution for the constant A, and for constant B we apply our second initial condition, which is velocity equal to 0 at time 0. But in order to do that, we need to take the time derivative of this equation 10, and here it is. This is the time derivative of the equation. And then we make it equal to 0 because the velocity at time equal to at time 0 is 0. So then this first term here is 0 and the second term is 1 because cosine of 0 is 1. So then we have b equal to 0. So now we have a and b. We just plug them back into equation 10 to get our very final solution. So this is the answer, or the equation that calculates displacement as a function of time. Okay, so this is the first task here. Now moving to the next task. So the next question is, okay, what is the maximum kinetic energy and the maximum potential energy? Well, the kinetic energy of the system is right here. Is 1/2 of the mass times the velocity square. So this is the kinetic energy. Now the potential energy is a summation of the gravity force between the gravity force and the spring force. So let me improve this a little bit. Make it look. So this is S for spring. Okay, so let's discuss. Well, actually, this is just a um, review, right? We need to calculate the potential energy of the spring, and the potential energy. Well, I mean, the first component here is going to be mgy, or mass times gravity times height, and the second one here is the potential energy of a linear spring, right? So we've seen that in another class, but just quickly here, let's review that. So this is the spring. We are applying a force here to stretch the spring. So this is the reference position. This is the stiffness. So when we apply the force, we have displacement, and in order to in this case here, we are assuming that the spring has a linear behavior. So the potential energy is going to be the area below this curve. Um, so calculating the work that the force is a um, doing or imposing on the spring, we have um, you know the load times the displacement from 0 to y. So this is basically dy is right here. Let me remove this markups first. So this is dy. Okay. And the force can be written as stiffness times y, or displacement. So this is the Hooke's law for the spring. And then integrating this equation, we get stiffness times displacement squared over 2, and this is going from 0 to y. So this is our potential energy for the spring. So this is we have seen this in more detailed in a previous class. So therefore, the total potential energy is mgy plus the potential energy of the spring, and this is at the initial position when y is equal to 0, because if you remember, this is a unstretched condition. So at y equal to 0, let me see, I have a drawing here. So that's where we are. We are right here, right? So we have some height and some height potential energy related. All right. So what is the total energy here from this initial condition? So we have the total energy as kinetic energy plus potential energy, and here we have the equation for the initial condition. So at initial displacement, actually. Now we know that when the kinetic energy is maximum, the potential energy is minimum, and vice versa, right? So with that in mind, in this case here, when the kinetic energy is 0, then the velocity is 0, and the total energy becomes the potential energy only, right? So now, if you consider the vibration amplitude from a with respect to the initial position at y equal to 0. So we have this oscillation up and down about this axis, let's say the frequency axis. So if we, take make the rate of change of the potential energy with respect to y, or the displacement equal to 0, we have the potential energy at the minimum when the displacement is minus mg over k. So this is the static portion of the displacement. So this is a the basically the position, the equilibrium, or the position of the particle at the equilibrium condition. So at this point we have the minimum potential energy. So that means the minimum potential energy is equal to the potential energy of the spring, and then we substitute this term into the spring potential energy to get the minimum potential energy equation. So in this case, the maximum kinetic energy is the total energy plus the minimum potential energy. So this is the Tmax for this problem. Okay, so we have Tmax. We have, let's see here. We have Vmax. Max and Vmax. Yeah, the Vmax is right here. Let me. So this is also solution of question B. All right, Vmax and Tmax. Now, let's change the reference position now. Let's consider the displacement from the equilibrium position. So we are not at the unstressed condition anymore, at the position associated with unstressed spring. Now we are going from equilibrium position, so the spring is stretched at the static equilibrium. So if we go from our previous initial position, we have some displacement, right, from a unstressed to a stressed spring, and that's the static load, or the static portion of the displacement. So this delta is the displacement of the spring. Okay, so Z is going to be the this portion, this static deflection, plus any displacement in the y direction. Okay, and we also know that, again, the potential energy is mgy plus the potential energy of the spring. So if we combine these two equations, we get so here I'm just plugging this equation into this equation to get this equation. So, and then we do some algebra and rearrangement. So don't forget that once you get here, this second order term is very small and it's constant, so you can just eliminate that. It doesn't affect results significantly. And then we get this potential energy here, which is consistent with the potential energy of the spring. So then the total energy is the kinetic energy plus the potential energy, which is equal to the initial potential energy, or the potential energy, not the initial potential energy, but potential energy at the initial position. So that's at z equal to 0. So physically, that means the maximum kinetic energy is equal to the maximum potential energy, which is equal to the total energy at the maximum height from the initial position 0. So here we have the maximum kinetic energy. As the mass move up down, up, when it hits this point here, you have kinetic energy at maximum and you have potential energy at maximum. Now, let's repeat this exercise, but now we're going to stop at the lower position. So here we have minimum potential energy and minimum kinetic energy when it changes direction. So at this point here, the minimum kinetic energy is equal to the minimum potential energy, and they are 0. They are equal to 0. And here is maximum. So this is the analysis, based on energy methods, the analysis for the vibration measured or analyzed, measured from the initial position from the equilibrium condition, from the displacement at equilibrium. And that's it. So this is the end of this subject. So we just reviewed, and I guess I provided some more information because I didn't have time to go over the whole thing during the last class. So now you have the complete modeling and simulation of a spring mass system, no damping involved, just a spring mass. So this is a free vibration. It's going to vibrate forever. In this problem, in this exercise. Okay?